I've already mentioned three elementary particles of the atom, the electron, the proton, and the neutron, but we have ways in which we can represent those. The proton is generally represented in this sort of way. The one down at the bottom is referring to the charge that the proton has. The one at the top refers to its mass. And if that's the case, if the top is the mass, how do we think about an electron? The electron has no mass in essence compared to the proton, but it has a -1 charge, and so we represent the electron in that way. The neutron has no charge, so we put a 0 down below and a 1 up above because it has a mass of 1. But three elementary particles that we deal with in nuclear chemistry is the alpha particle, and the alpha particle actually has a total mass of 4. It has 2 protons in it. So in essence, this is a helium nucleus, 2 protons and 2 neutrons. We also have the beta particle. It is not a very nice beta, but you get the idea. A beta particle is in essence an electron. And then lastly we have a gamma particle, and a gamma particle has no mass and it has no charge. It is simply like an X-ray or like visible light or infrared light or UV light, except for it is one of the highest energy light particles that exists, right? So how did we come up with these? It turns out that way back when nuclear rather the elementary particles of the atom were discovered, they were put into a lead box, and the uranium actually was sitting in a pile down at the bottom of the box, and they had some photographic film over on the right, and it turns out that these particles kind of escaped through here and came out and hit this photographic plate, and we saw light on that photographic plate. Then they put a magnet around the particles that were coming out of there, and one side of the magnet was charged positive and the other was charged negative. And so then you could imagine what's going to happen when a beta particle comes through here, right? The beta particle, being negatively charged, is going to go toward the protons. And so as it came out, I'll do this one in red, as the beta particles came out, they came along the same trajectory, but all of a sudden then started being attracted toward that positive plate of the magnet. You could imagine what happens when the alpha particle came out. The alpha particle came out just like the others, but then it got attracted to the negative plate, but it was not affected quite as much because it was much heavier, much like if you have a light car trying to take a curve, it's going to be affected a whole lot more than a heavier car. A heavier car you can't turn quite as quickly, and so we ended up with the alpha particles, we ended up with the beta particles, and we ended up with the gamma particles. So that's where all of that came from. You can also see what happens when you take a proton and react it with an electron, that if you were to add these two particles together, a 1 plus a 0 up on top gives you a 1, and a 1 plus a -1 down at the bottom is going to give you a 0. Well, the thing that is 0 on the bottom and 1 at the top is a neutron. So a neutron is in essence a proton plus an electron, and we'll use that kind of very simple math as we go along. You've heard of carbon-14 dating before. Where does carbon-14 come from? Actually, carbon-14 comes from nitrogen in the atmosphere. So this is the symbol for nitrogen. It's got 7 protons and 7 neutrons. In the upper atmosphere, it can interact with neutrons, and when this happens, what we end up getting is carbon-14, right? And so you should be able to guess now what is the other byproduct of this nuclear reaction, right? So at the bottom we see 7 plus 0, so that's 7, and on the product side we have 6. We've got to come up with something else that has a 1 down at the bottom, and at the top we've got 14 plus 1, and so on the products we have to have 14 plus 1. So now the question is, what is 1 and 1? 1 proton at the bottom has a mass of 1, so this is a proton. So this is where carbon-14 is coming from. What about uranium-238? It turns out that uranium-238 is not quite as stable as it should be. It should fission because it wants to work its way toward iron, and so uranium-238 can be represented this way, but we like to put the number of protons on there as well so that we can balance these nuclear reactions. If we look at the periodic table, we can find that uranium has 92 protons, right? Uranium-238 will react with a neutron as well, like so, and it turns out that, well, actually, let me bypass this one here to start with. Sorry. We will take that out, and I want to first of all just look at uranium-238 giving off a alpha particle. So if it gives off an alpha particle, so I can either write a helium there or I can write an alpha. What is the other product that we're going to get from this, right? So this ought to be a simple one, right? 238 is made up of 4 plus 234. And then 92 is made up of 2 and 90. So now I've got to look on the periodic table and find out what it has 90 protons, and that is thorium. So this is a balanced chemical reaction of uranium-238 simply falling apart by alpha elimination. The other reaction that I was just about to do was a uranium-238 I'm sorry, uranium-235. Let me try that again. Uranium-235. And again, uranium is 92 protons. And that can react with a neutron. And it turns out what you get from that is 3 other neutrons. So this is what we're going to refer to as a chain reaction a little bit later on. But we get 3 neutrons from that. We also get bromine 87, and bromine has a mass, or rather a number of protons of 35. And so now you ought to be able to tell me what that third particle is that you get from this, right? So 87 plus 3 neutrons, so that's going to be a total of 90 for a mass. So 235 plus 1 is 236. I got to subtract 90 from that. I'm going to get 146. So 90 from 235 and 1. So 146 is my total mass. And then on the bottom we've got 92 plus 0 on one side, and 3 times 0 is 0, and we've got 35. So 92 minus 35 is 57. And we can look at the periodic table to find out what element 57 is, and that happens to be lanthanum. So our balanced chemical equation would look something like, sorry, I chopped off my 235 there for the uranium, but that's a balanced reaction, a balanced nuclear reaction.